Okay, welcome back, folks. We've covered a lot of material recently, and I just thought that it would be a good idea to start with a recap of some recent ideas, some recent concepts and formulas. So uh, we talked about the acceleration theorem, basically Newton's second law for these Bloch electrons. As you remember, Bloch electrons, that's just my shorthand for electrons that are experiencing a weak periodic lattice potential, right? So they're not exactly free. They are in the context of a lattice environment, an ionic lattice. And so for those kinds of electrons, we were able to derive this acceleration theorem, which is basically just Newton's second law, namely that h bar times the change in time of the k vector is given by the sum of external forces. Now we can, of course, now introduce this crystal momentum P sub c, as just h bar times k. And this formula can be written then as P sub c dot, or dpc over dt. That time derivative is equal to the sum of external forces. So that is exactly then in the form of Newton's second law. But here it is important to remember that the external forces that appear in that formula exclude anything that's coming from the lattice. These are external forces, but not forces that act on the electrons that are coming from the ions. Those are excluded and not considered here in that sum of forces. Okay, and so we also introduced a notion of velocity for these Bloch electrons. Here we said we're not dealing with the phase velocity, but rather sort of the group velocity idea. And we introduced this formula that the velocity of a Bloch electron is given by this gradient in reciprocal space of the energy, right? So 1 over h bar times this gradient. And I have a little subscript k to remind ourselves that this gradient is to be taken with respect to the reciprocal lattice vector. Okay, and so we see here that the velocity is simply just proportional to that. Okay, and so with these two formulas then, we can derive the following relationship, and we were able to do it fairly quickly, namely that the acceleration that such a Bloch electron experiences can be written in terms of the external force. Remember, this external force is basically an applied force that comes in from the outside. It's not internal to the crystal. All right, and so then what's nice is that this allows us to introduce this idea of effective mass, m star, for the Bloch electrons. And this m star being basically inverse to the second derivative of the energy with respect to the wave number, right? So in one dimension. So it's basically inversely proportional to the curvature of the energy band. So that's what we said. And I wanted to sort of add a little bit more commentary to those results before we look at actual applications, or how we actually apply these ideas to real situations. I wanted to spend just a little bit more time on interpretation. So first, what is up with this P sub c, this crystal momentum? What is it, and why do we need the subscript? Well, we need the subscript because P sub c is not equal to the full momentum of the Bloch electron. Okay, so because we said, so semi-classically we argued that P being m times v is not equal to h bar times k, right? We said actually that v is not even parallel to k in general, the two vectors not being parallel, and so we cannot have that equality. So that is what we saw earlier, okay? But there's also another quantum mechanical reason that I'm just going to mention in passing here, namely that the Bloch wave function is just not an eigenfunction of the momentum operator, simply. So the full momentum operator being minus h bar, I times h bar times del, right, ddx. So if that didn't make any sense to you now, then wait until next semester for the upper level quantum mechanics course. But in any case, we have multiple justifications for why the full momentum cannot be set equal to h bar times k when you have a crystal potential energy that the electrons feel. Okay, so we have to make that distinction between P and P sub C, but we kind of need to dig a little bit deeper. What is that distinction really all about? And the best way to understand it is through Newton's second law. And so classically speaking, we have Newton's second law is valid. So F total is equal to the change of the total momentum, the full momentum with respect to time. So this total force includes all the forces that are exerted on the electron, and which also includes then the forces that the ions exert on the electron, right? So the lattice ions will, of course, exert forces on the electron. Why? Because they give rise to the potential energy landscape in the first place. Okay? And so F total would have to include that, as well as any kind of external applied force, like due to an electric field or something like that. Okay, so now contrast that with this, this formula here. It looks very similar, but here I'm not calling it F total, I'm calling it external force, external to the entire crystal. And then instead of the full momentum here, we're now going to use the crystal momentum. Okay, so the ionic forces on the electron here would be excluded from the left side. So the upshot is that when we ignore the lattice or ionic forces, then we can write down a simple formula, namely that the external force or the sum of external forces is equal to h bar times this time derivative of the wave vector k. And so how is that? How can that be possible? That by ignoring a complicated force, we get something fairly simple. Well, it turns out that the lattice forces have sort of already been indirectly accounted for via the dispersion curve or the band structure. It's already in there, it's already built in. And so now the formula is actually quite simple to write down. All the work went into sort of predicting the shape of the bands, the various bands. And once we have that, then we can ignore the lattice forces and deal only with additional forces. And we get a fairly nice and simple equation, okay? So this formula is also very powerful for that reason. You know, we don't have to worry about the detailed forces at play that act on the electrons due to the ions. This would be very difficult for us to nail down in any case, because these forces have already been folded into the band structure and therefore also the effective mass. Okay, so that's sort of the bigger idea. So let's return now to this other question, namely, what is this all useful for? Why are we doing this? All right, so the best way to motivate it is via an example, and the simplest example I could think of is Bloch electrons that are subjected to a constant electric field. So if you have a free electron that feels a constant electric field, well, it just gets accelerated, you know, sort of in an old vacuum tube, right? You can get these electrons, you know, just accelerate them between two plates in an accelerating potential. So, you know, that would be sort of a free electron. Okay, they get accelerated in a line. But what happens with these Bloch electrons when you have that sort of happen inside of a crystal lattice? Well, The external force then is just E times this electric field. Our book uses the convention that E here is a symbol that is a negative 1.6 times 10 to the negative 19th coulombs. Okay, so the negative sign is built into the symbol. So then we can say, using the acceleration theorem, that the change in wave vector over time with respect to time is equal to just E over h bar times that electric field. So very simple equation, and we can integrate that equation very easily as well, okay, to arrive at the time dependence of the wave vector, right? So this is now a time dependent, the explicit time dependence of, so I could say k of t here as well, if I wanted to. And use a different color here. Yep, so this is a explicit time dependence of the k vector, right? So here's the time, here's the electric field, okay? Here's a constant E over h bar, but here's it's basically linear in time. And we have a constant of integration called k naught. So that's where we start out at time is equal to 0. Time is equal to 0, the k is equal to this k naught. And then we basically just march in the direction of the electric field. Well, against it really, because E is negative, right? So if little e, so this is here my electric field pointing up. Here's where I start out with a particular Bloch electron, okay, right here, and then it will march steadily against the direction of the electric field in time, right? So that's basically what that formula tells us, and we can look in one dimensions now really quickly too. Okay, so in one dimension, of course, I can only have that electric field pointing right or pointing left. Here I chose it to point to the right. Okay, and let's also start out with an electron. So sitting here at the origin at k is equal to 0. Okay, what happens? Well, not surprisingly, it's going to go to the left, that electron, right? So after some time, it's going to be here. Okay, some time has elapsed, delta t. Then a little more time has elapsed, another delta t. Now it's at 2, another delta t. Now it's at 3. So it's marching steadily to the left. Okay, the electron moves to the left in k space or in reciprocal space. All right, so but how does it move in real space? That's really kind of the more consequential question. We know how it moves in k space, that's a simple formula, but how does it move sort of in real space? So we need to figure out what the velocity of that electron is going to be, but it is actually given by this derivative dE dk, right? So that energy derivative with respect to wave number is what our velocity is determined by. So really what we have to do is we have to find these slopes. This slope of the tangent line to that dispersion curve, to that band. And so we see that those slopes are all negative, right? They're all sloping down. That also means then that the velocity is negative. And this is really good. This is good news because we have an electric field that is positive. In other words, it is pointing to the right. And so when we have an electric field that's pointing to the right, it's kind of good that the electrons will be moving to the left. Remember, they have a negative charge. Okay, so that is good. Now, remember, this is now real space, right? This is a velocity in real space. Whereas k dot or dk over dt, that's the time derivative of the wave vector. So that's how it's sort of moving in reciprocal space, not in real space. But when we look at the slopes, then we get how the particle would be moving in real space. So it's sort of a two-step process here. Okay. So if you look at the detailed velocity in time, okay, so how does the velocity sort of evolve in time? And then you notice that at first the electron is speeding up to the left, but then as we sort of get closer to the zone boundary of the first Brillouin zone, then it's slowing down again. You see that very clearly from the dispersion curve, right? And so at k is equal to minus pi over a, so when we've reached the zone boundary there, of course, the lattice, we said, strongly scatters the electron wave, and so we don't get a velocity there. That's what we said actually way back when we said that that is one of those magic wave numbers where Bragg scattering really happens very prominently, and so we get sort of no velocity because the electron is moving to the left. Well, then, and the Bragg condition is satisfied, then we get backscattering in one dimension. Okay, so it's important though to keep in mind that that does not imply that we stop marching to the left in k space. Remember, because the derivative dk dt or k dot never changes at all. It's always constantly negative. So we keep marching to the left. Okay, and so what happens, what would happen when a k then pretty quickly crosses that zone boundary minus pi over a? What happens then? Well, you probably guessed it, it emerges at k is equal to plus pi over a, because we can shift things back into the reduced zone, right? And so it emerges back at k is equal to plus pi over a, where it would also have actually a zero velocity there momentarily, but then we move further to the left and all of a sudden it has a positive real velocity, okay? So what you sort of see here, maybe, perhaps, emerge is that we get sort of oscillatory motion. As we're sort of zipping around, okay, we're going all the way to the left of the first Brillouin zone and then emerge back on the right and keep going to the left, merge back on the right, keep going to the left. And as we're sort of traversing that, sometimes the velocity will be positive and other times it will be negative. So we have sort of this oscillatory behavior in real space. So, which is interesting because a constant electric field, okay, would then produce electrons in the lattice that are oscillating in space. Okay, so there's going to be a homework problem on that very point. One caveat is that we would have to assume that there is no scattering at all, and that assumption is probably unrealistic. But if we could set it up so that the electron isn't scattered by any kind of imperfections or by any kind of lattice vibrations, okay, so at very low temperatures perhaps, then we should see that oscillatory behavior. But normally, okay, under normal circumstances where we're not at cryogenic temperatures, we do get scattering, and actually from the Drude model we know that that relaxation time is actually very short. So these scattering events happen very rapidly in succession, and so that assumption is normally not satisfied. So then the question has to be reframed a little bit. We could ask, how far to the left in reciprocal space can an electron move before it is scattered? Okay, that is a question I want to address now. Okay, so how far to the left in reciprocal space, and we're going to call it delta k sub x. All right, and so, well, we have the formula. It's basically E times that electric field over h bar times how much time we have for that process, right? And how much time do we have? Well, on average, we have about one relaxation time of time. And so then we actually have a formula for how far to the left we can move as an electron before something else happens. Okay, so relaxation time. Okay, so now let's apply this not just to a single electron, but say to a half-filled or partially filled band of electrons, like what we would get for a monovalent metal. Okay, so there we have this band and it's sort of half filled or partially filled. We go up to the Fermi energy, we said, right? Everything is filled up to the Fermi energy and everything beyond that is empty. Okay, so this is sort of before. Okay, and then we apply an electric field. Okay, and so then things shift, right? This is after a time tau. Things electrons have been able to sort of shift to the left by a certain amount. Okay, and so now we have this sort of this imbalance here, right? There's more electrons on the negative side of the k-axis as there are on the positive side of the k-axis. And so we have sort of a shift of every electron to the left by an amount delta k sub x. Now, the question is, how much current do we now get? Okay, it's very clear that we would get a net current now well, the current would be to the right, but the motion is of the electrons is to the left. There's just more electrons that have negative velocity now than there are with positive velocity. Okay, so what is sort of the net current? Can we estimate the net current that we get? And we just go back to the basic formula for current density, right? NEV is the formula we remember. Okay, and so I have that here, but I call this n prime because the n here is a particular n that I want to highlight here in a moment. But first, what is this? And the v here is not just any speed, it's the speed of the electron at the Fermi energy, or the velocity of the electron at the Fermi energy. Okay, so it's basically this v sub f really refers to the velocity of these electrons here. Okay, that sort of give you the excess, okay, the imbalance of those electrons is what I'm highlighting. So the velocity here, and then this n prime is just the number density of electrons also at the Fermi energy. So I guess I could have called it n sub f here as well. Okay, so the prime here is just it's not indicating a derivative or anything. So it's just just a symbol to remind me that I'm talking about a particular number density. All right. So here is where it gets just a little bit technical, and you just have to sort of stay with me at this point. We're going to introduce a new quantity that the book unfortunately labels capital N of E. Okay, so this is a capital N of E. It's the number density of electrons at energy E per unit energy. Okay, so such that if I multiply by some energy interval, okay, delta E, then this combination N of E times that interval gives me an actual number density of electrons. Okay, the number density of electrons that reside at energy E, or that have energy E. Okay, so what units does N of E have? Well, it has units of 1 over meters cubed per joule, okay? So it's not just a pure number density now. A pure number density, little n, would have just 1 over meters cubed, or 1 over a centimeter cubed. But here, we have to remember that this is also per unit energy still. Okay, so we have the joules here, or the electron volt here in the denominator as well. Okay, so with this definition, or with this choice of N of E, then we can write EVN or NEV a little bit differently. We can say, all right, this N here, this little n, the number density is really the number density, this capital N at the Fermi energy times a little energy interval, okay? So far so good. So we've basically replaced the N prime here with this thing here, okay? All right, so then I can work a little bit on the delta E. I could write that as the the energy derivative, okay, times delta K. All right, so here it is again. That's where we're at. Okay, we've written it like this. Now, this here, we know to be simply just h bar times the velocity, right? That's actually how we define velocity, as 1 over h bar times that derivative, right? So that is just h bar times v, and not just any v. We're talking about this derivative is evaluated at the Fermi energy, so that has to be the velocity at the Fermi energy. I'm going to call it v sub f. Okay, so then we get that. All right. So I can put these two v sub f's together, get a v sub f squared, fine. And next I want to sort of work on this delta k for a little bit, because what we just have derived a formula for delta k, right? So that was how far to the left can an electron actually move in a time equal to the relaxation time tau. And we said it was E times the electric field over h bar times that tau. And so I'm going to plug that in, and I get then this formula here. Okay, so that's what I get simply when I follow the math. But then I remember also that Ohm's law says that the current density is equal to the conductivity times the electric field. And so when I compare those two equations there, I do have to conclude that the conductivity here is given by everything out front of the electric field, all these constants here out front. That is going to be my conductivity. Okay, so that is a formula that the book also derives, okay? There is maybe a slight subtle point that I want to highlight here. I'm not sure if the book does, but I kind of want to highlight it. We see that we have this, the reason that we have a current in the first place is because we have an imbalance, right? There's more electrons on the left than on the right, fine. But what is that imbalance? Well, we see that there is a complete balance from here up to here, to this point, right? So this would be completely balanced. And then all the electrons in here are going to give rise to the net current, right? So all the electrons that find themselves in this interval on the k-axis. Now that interval actually turns out to be 2 times delta k sub x, right? Because we shifted every electron by delta k sub x, but then this imbalance here is 2 times that. So shouldn't there be a factor of 2 in here, right? So these are all the electrons that give rise to a net current, we said. And so from that point of view, you would expect maybe instead of E times the electric field or h bar times tau, maybe twice that. But it turns out that that factor of 2 is exactly canceled out by another small error that we made. Namely, we said we needed this n at the Fermi energy, okay, but the Fermi energy is also here, okay. We really just need the Fermi energy. We need those electrons that are on the left side, not on the right side, and so there's another factor of 2 that just cancels that factor of 2, and the previous formula stands. Okay. So you can look for more details in the book, how we do this in 3 dimensions. Okay, it's not really all that complicated, but we do get a prefactor of 1/3 in 3 dimensions. Okay, so but the rest of the formula is exactly the same. Okay. On the homework, I will have you show that this formula is dimensionally correct. Okay, it gives you the right dimensions for conductivity. Now, we can call this formula the quantum formula for conductivity, or some people also call it the semi-classical formula for conductivity. So a semi-classical is an improvement over fully classical, right? So we're already making use of some quantum concepts here. And so remember though that the fully classical formula coming out of the Drude model for conductivity was given earlier in the course by NE squared times tau over m. Okay, and so it looks quite different from the formula we just derived now. Although there are some similarities too. There's an E squared times a tau, and that's also in here as well. And then there's some kind of number density here, and then there's this capital N of E here. There's some overlap, but it does look quite a bit different. Now, when we compare the two formulas, we see that sort of this N here, this little n, as number density, is replaced now by sort of m times v f squared times this capital N of E. So we don't get the mass in the denominator here, right, in the quantum formula. And so what is sort of the interpretation there? What's the what's sort of the conceptual picture? Well, we said that in the classical formula we had n. In the quantum formula we have sort of this beast here, where this is sort of the kinetic energy at the Fermi level, right? And then this is the number density per unit energy at the Fermi level. Okay, so the upshot really is that the big difference between the classical and the quantum formula is that the conductivity is now mostly dependent on the number density per unit energy, this capital N, at the Fermi energy. So how many electrons, loosely speaking, do we get at the Fermi energy? Whereas the classical formula doesn't care what energy the electrons have. Okay, all of them contribute to the conductivity. So we're not so much interested in how many total valence electrons, free valence electrons, do we have in the metal. We're more interested now in the quantum equation or the quantum formula we're more interested in how many electrons are there near the Fermi energy. The rest, so it's not that important for us. The rest sort of balance each other out. You see what I'm saying? The rest sort of balance each other out, and it's really just the number density at the Fermi energy that really decides how conductive the metal will be. Okay, so next up in the next lecture, we have to look a little bit more at this quantity here that we've introduced, this N of E. And we have to get a handle on it because we'd like to estimate what it is. You know, if we want to plug things into the quantum formula, we're going to have to know what to plug in for capital N of E. Okay, so that's going to take us another lecture to sort of straighten out, but we're getting there. We're sort of moving from the classical formula for conductivity from the Drude model to a more accurate formula that comes out of the quantum mechanical description of electrons. Okay, thank you.